In the previous section, we discussed the asymptotic notations, and we also learned that the most important asymptotic notation is the big O notation. In this section, we will be learning how to compute the time complexity of a given code, in particular a given function. This is essential for coding interviews, and it is equally important in your day-to-day development in the company. The popular time complexities that we consider in the increasing order of their time are constant notation, logarithmic time, linear time, which is big O of n. N log n is also important because it is the time complexity of major sorting algorithms like quicksort and merge sort. Then comes the polynomial time complexity. You can argue that even the linear time complexity is polynomial of degree 1. For that matter, you can even say that constant time complexity is a polynomial time complexity of degree 0 because 1 is n raised to the power 0. But here, when we say polynomial time complexity, we are considering the powers of n which are greater than 1. Then comes the exponential time complexity, and finally the factorial time complexity. So constant time complexity is the minimum asymptotic time complexity, and the factorial time complexity is the maximum asymptotic time complexity. There may be other time complexities which are a combination of these time complexities. For example, n raised to the power log n. In computer science, most of the times we will be writing log as lg instead of log. In mathematics, most of the time the base of the logarithm is 10. But in computer science, most of the times the base of the logarithm function is 2. So lg of n essentially means log of n to the base 2. As a rule, you can understand that logarithmic time is better than any power of n. For example, the asymptotic time complexity log n is small o of n raised to the power k, where k can be any small number. So even if it is n raised to the power 0.000001, it is still considered greater than log n for n being very, very large. Consider this example. This is the question which was asked in the GATE exam. Here we are given three functions. f1 is 10 raised to the power n, which is the exponential function. f2 is n raised to the power log n, and f3 is n raised to the power under root of n, square root of n. We have to arrange these functions in the increasing order of their asymptotic growth. We clearly know that exponential time is greater than any polynomial time. So 10 raised to the power n is probably the greatest. Therefore, we can discard b and c. Now f2 is n raised to the power log n, and f3 is n raised to the power root n. Because these two n's are same, so essentially we will be comparing log n and root n. Now root n, we know that root n is n raised to the power 1 by 2, which is equal to n raised to the power 0.5. So there is a comparison between log n and n raised to the power 0.5. Now we know that asymptotically log n is less than equal to n raised to the power 0.5. Therefore, the correct order is f2 is the minimum time, f3 is asymptotically greater than f2, and f1 is the greatest. Another way of comparing these functions is that you find the log of all of these three functions. So the log of this number is n log 10. The log of this number is log n into log n. And the log of this number is square root of n into log of n. Clearly, this is a linear function. Now this is log square n. This is order of n. This is log square n. And this is square root of n into log n. And this function is a linear log function where square root of n is multiplied with log n. Clearly, log n is less than square root of n. So the multiplication will be less than square root of n into square root of n, which is essentially n. So you will come up with the same conclusion. As I said, these are the main functions. So there are combinations also. Like you can have log of log n. Similarly, you can have log n whole square. As I said, constant, logarithmic, linear, linearithmic, polynomial, exponential, and factorial. These are the main functions, but in between you can have log of log n. So log of log n stands in between logarithmic function and constant function, which means that it is greater than constant but less than logarithmic. Similarly, log n square is greater than logarithmic because it is square of logarithmic, but it is less than linear. And any power of n which is greater than 1 will be better than n log n. So it essentially means that any power of n, irrespective of how small it is, will be greater than log n. Now let us look at the code of these time complexities. Consider the following function. This function square takes a single parameter and return the square of that number. Here the size of input is constant because the function is receiving only one variable. Whatever is the value of the input parameter, the multiplication is going to take the same time. Therefore, the time complexity of this function, the asymptotic time complexity of this function, neither depend on the size nor on the value. It does not depend on the size because size is constant, and it does not depend on value because the operation is constant. The size of input values is not going to change. This function will never receive 2 parameter or 3 parameter or variable number of parameters. And it does not depend on the value because all the operations performed inside the function are not dependent on the value of the input parameter. Consider another function. Now this function also receives only one input parameter, and this input parameter is also an integer variable. Therefore, in this case also, the size of input is constant. But even though the number of parameters is only one, this for loop will iterate n times. So the value of n becomes important because if n is 100, this for loop will iterate 100 times. And if n is 0, then this for loop will not iterate even once. Therefore, the time taken by this function is directly proportional to n, and we will say that this function takes time, which is big O of n. You can also say that the time taken by this function is theta of n, which is also correct. But since we are considering only the big O time complexities, we'll call it big O of n. The important thing to note here is that the asymptotic time complexity of a function either depend on size of the input or depend on the value of the input or depend on both. Consider this function. This function is also receiving only one input parameter n. The outer loop inside this function is executing exactly n times, but the inner loop is executing only 3 times. So I will vary from 0 to n minus 1, but for every value of I, j will go from 0 to 2, which means that j will execute 3 times, and every time it will print a star. Therefore, this function is printing 3 stars in every line. So after printing 3 stars, we will move out of this inner while loop and we will go to cout, which will print a new line character. And then in the next line, again, we are printing 3 stars. Then in the next line, we are again printing 3 stars. And this will keep on going for n such lines. For n such lines, we will be printing 3 stars in every line. Now you may argue that why are we having this inner for loop? We can just print 3 stars here itself. You are correct, but we are not getting into the optimality of this code. We are trying to find out asymptotic time complexity of the existing code. So in the existing code, this body will take constant time because 3 is constant and the only variability is in the outer loop. So the outer for loop will execute n times, and in every iteration of this loop, this will take constant time. So the total time taken by this function is big O of n. If you change this function a little bit, and if you accept 2 parameters, let's say it takes another variable m, and this loop is getting executed m times. For this function, the outer loop is still executing n times. The outer loop still execute n times, but now this inner loop also takes m time because this loop is iterating m times. So we are printing these m stars in every line. The number of columns are also variable, and we are printing m such stars, and the number of rows are also variable. We are printing n rows. So the total number of stars which will get printed will be n into m. This cout statement will execute m into n times, and the total time complexity of this function is also big O of m into n. You will notice that the asymptotic time complexity of a function is directly proportional to the statement which is getting executed the worst case number of times. In this case, for example, this condition will be checked only n times. This increment will happen only n times. This initialization will happen only once. But this print statement will be printed m into n times. The time complexity will be governed by the statement which is getting executed maximum number of times. Therefore, inside a function, you need to find the statement which is executing the most number of times, and you need to find how many times is that statement getting executed, and that will give you the time complexity of that particular function. Let's change this function a little bit. What if we are having only one input parameter, but the inner loop is getting executed I times? Now again, in this case also, the outer loop is getting executed n times, which means that there are n rows. For the first iteration of the for loop, value of I is 0. For the second iteration of the for loop, value of I is 1. Similarly, for the last iteration of the for loop, value of I is n minus 1. Now, what are we doing inside this for loop? inside this for loop, we are printing star I times. It means that in the first line, star will be printed 0 times, which means that nothing will get printed. In the second line, star will be printed I times again. So it means that 1 star will be printed. In the third line, 2 stars will be printed in the same line. Then in the next line, 3 stars will be printed, and so on. In the last line, n minus 1 stars will be printed. So how much time do you think this function will take? Again, we have to look at this cout statement, because this cout statement is the statement which is getting executed the maximum number of times. Now, how many times is this statement getting executed? For I is equal to 1, this statement will execute 1 time. For I is equal to 2, the statement will get executed 2 times. For I is equal to 3, the statement will be executed 3 times. For I is equal to 4, the statement will be executed 4 times, and so on. For the last value of I, which is n minus 1, this statement will get executed n minus 1 times. So the total number of times this statement will execute will be summation of n minus 1, that is equal to n minus 1 into n divided by 2. This is a simple summation formula which you will get from the mathematics. This will come out to be n square by 2 minus n by 2. If we find the asymptotic notation of this equation, it will be big O of n square, because we will be considering only the highest power. So this code will take big O of n square time. Even this code, when the inner loop is getting executed n times. So the outer loop is executing n times and the inner loop is also getting executed n times. It means that we are printing n stars. So in every line we are printing n stars. So this piece of code will also take order of n square time. So which code is taking less time? When we have n here or when we have I here? Obviously, when you have I here, will be n square by 2 minus n by 2. But when you have n here, then the number of stars which will get printed will be exactly n square. So the constant factor of these two will be different. But asymptotically, both of them are order of n square. We must not confuse the absolute time taken with the asymptotic time taken. Absolute time taken is the real time taken, whereas asymptotic time taken is the proportional time taken. How the time varies with respect to either the size or the value of the input parameters passed to the function. Now consider this code. This function is taking one parameter n. The outer loop is getting executed n times, and only when I is 10, only for I is equal to 10, the star will get printed. Otherwise, the star will not get printed. Let us remove even this statement. So this function will print only one star, and that too when I is equal to 10. If the value of I is less than 10, then it will not print even a single star. So what should be the time complexity of this function? Clearly, in this case, you cannot find the time complexity from this cout statement, because this cout statement is getting executed only once. That too when value of n is greater than 10. If value of n is less than 10, then the statement is not getting executed even once. So this is not the statement which is getting executed the maximum number of times inside the function. This condition is being checked n times. This increment happens n times. This condition is being checked n times. And this initialization happens only once. Now when I say n times, I mean big O of n. For example, this condition is not checked exactly n times. This condition will be checked exactly n plus 1 times. After the last iteration of the loop, this condition will be checked, and when this condition becomes false, then we move out of this while loop, this for loop. So the condition will be checked exactly n plus 1 times. But we say that this is checked n times because we ignore the constants. So if you ignore the constants, then you can figure out that the time complexity of this piece of code is also big O of n, because the conditions are being checked n times. What I'm trying to say is that the statement which is getting executed the maximum number of times may not be the same statement which is inside the maximum indentation. It is a similar function. The only difference here is that I is getting incremented by 2 instead of 1. So I is equal to I plus 2. The initial value of I is 1, then I will be 3, then I will be 5, then I will be 7, and so on. When I becomes greater than n, then we stop. So this for loop will execute n by 2 times. This condition will be checked n by 2 times. This star will be printed n by 2 times. And this increment will also happen n by 2 times. So we can say that the time complexity of this function is also n by 2. And because order of n by 2 is order of n, so we will say that this function takes big O of n times, because n by 2 is order of n, because we ignore the constants. Now, what if we change this a little bit and we change this addition to multiplication. So instead of this addition, what if we have multiplication? It means that I is equal to I into 2. Let us see how many times is this function getting executed. Let's say n is 32. Initially the value of I is 1, then the value of I will be 2, then the value of I will be 4, then the value of I will be 8, then the value of I will be 16, then the value of I will be 32, then the value of I will be 64, and so on. It means that I is doubling itself for every iteration of this loop. So by when will I reach n? Consider it with an analogy. Let's assume you have a forest, and in this forest there is a poisonous plant. So this is the poisonous plant. So this plant has poison, and let us assume that there is a property of this plant that this plant doubles itself every day. So on the first day there is only one plant, on the second day it will double itself and there will be two plants. On the third day both of these plants will double themselves, and now we have four such plants. On the next day all of these four plants will double themselves, and now we have 8 plants. So each plant is doubling itself every day. My question to you is that if it is a very big forest and it took the plants to capture half of the forest in 1 year. So after 1 year, these poisonous plants have spread in half of the forest. My question to you is that how much time will it take for these poisonous plants to spread into the entire forest? So if these poisonous plants have become equal to x, where x is a very large number, in let's say 1 year, then after 1 day it will become 2x. It will take only 1 day for the poisonous plant to cover the entire forest. This kind of growth is exponential growth, when a variable is multiplying itself for every iteration of the loop. In the first iteration, the value of the variable is 2 raised to the power 0. In the second iteration, the value of the variable is 2 raised to the power 1. In the third iteration, the value of the variable is 2 raised to the power 2, and so on. In the fourth iteration, it will be 2 raised to the power 4. In the kth iteration, it will be 2 raised to the power k minus 1. It will take only n time for this variable I to reach 2 raised to the power I. Because the variable is growing exponentially, it will take the variable only log n time to reach the value of n. It means that this for loop will execute only log n times, because after log n iterations, the value of I will become equal to n. I hope you are able to understand, but let us try to revise this concept so that we are able to understand the relationship between exponential and logarithmic time complexities. If the value of variable I is equal to 1 and I is doubling itself, then after the second iteration I will be 2. After the third iteration I will be 4. After the next iteration I will double itself and it will become equal to 8. After the next iteration it will become equal to 16, and so on. You can see that the growth of the function here is like a complete binary tree. In a complete binary tree, you have only one node at the root, but at the next level, number of nodes are 2. In the next level, number of nodes are 4. In the next level, number of nodes are 8. With every level, the number of nodes are doubling itself. Now, the number of nodes at this level is equal to sum of number of nodes at all the previous levels minus 1. It means that if this level is 16, count of all the previous nodes in all the previous levels is 16 minus 1, 15. Similarly, if this level is 8, then the count of all the previous nodes in all the previous levels is 8 minus 1, 7. If the count of this level, if the number of nodes in this level is 4, then the number of nodes in all the previous levels combined will be 4 minus 1, 3. If every node here represents a function call, then you can say that total number of function calls at level k is equal to total number of function calls up to level k minus 1. This is the exponential growth. Now this exponential growth has a relationship with the logarithm. Here we have this exponential growth. So 1 is becoming 2, 2 is becoming 4, 4 is becoming 8, 8 is becoming 16. If we have exponential growth, then to reach the number n, we will take only log n steps. This is the relationship between exponential and logarithmic. If we have exponential growth, then to reach a particular number, the total number of steps taken will be logarithm of that number. So if you have a complete binary tree and the number of nodes in a complete binary tree is n, then number of levels in the complete binary tree will be log of n to the base 2. And you must have noticed in binary tree, whenever you are dealing with levels, the number of levels in a binary tree are assumed to be log n, because we assume the binary tree to be balanced binary tree. Let me give you one more interesting way of looking at it. We have seen the concept of doubling. Now let us look at the concept of halving. Let's say you have a number 32, and every time we half this number, in the next iteration the number will become 16, in the next iteration the number will become 8, in the next iteration the number will become 4, in the next iteration the number will become 2, and in the next iteration the number will become 1. So if we are halving the number, then we are moving in this binary tree upside down. In the last level you have 16, then if you half it, then you are at 8. If you half it, then you are at 4. If you half it further, then you are at 2. And if you half it further, then you are at 1. So if we keep on reducing the number, after log n iterations, the number will become equal to 1. So if you have a number 1024, then after 10 iterations, the number will become 1 if we are dividing the number by 2. You notice that there is a relationship between doubling and halving. Therefore, doubling is the exponential growth and halving is the exponential reduction. If you have exponential reduction, then the time complexity will be logarithmic. So this is how logarithmic and exponential are related. Let us look at the same code again. If we change this condition to I is greater than equal to 1 and make it equal to I is equal to I divided by 2, then also the for loop will execute log n times. In the first case, we were incrementing it and we were doubling it. In the second case, we are halving it. In both the cases, it is taking log n time. Let's look at another function. In this function, you will notice that the outer loop is getting executed n times and the inner loop is getting executed log n times for every iteration of the outer loop. It means that the total time taken by the function will be n into log n. The function will take big O of n log n time. This is the time complexity of both quicksort and merge sort. In case of merge sort, we divide the array in two parts. Dividing the array takes n time, and then we process these two parts separately. So processing these two parts means that we are having two problems of half the size. Initially, you have one problem of size n. Now you have two problems of size n by 2. Both of these problems will be broken into half of their size, which means that now you have 4 problems of size n by 4. And this breaking up of the problem into half of their size will continue till the size of the problem becomes equal to 1. We know that the size of the problem will become equal to 1 only after log n levels. It means that total number of levels in this function called tree will be log n. At every level, we are taking n time to break up that array into two parts. So at the first level, the total time taken will be n. At the second level, we will be taking n by 2 time to break this subarray, and n by 2 time to break this subarray. So the total time taken at this level is also n. Similarly, the total time taken at this level is also n. At every level, we are taking n time, and there are total log n levels. It means that the total time complexity is n log n. The following recursive code finds the nth term of Fibonacci. So this function receives an integer variable n, and for that integer variable, it will find the nth term of Fibonacci. Fibonacci is a sequence where every term is the sum of previous two terms. The first two terms are 0 and 1, then 0 plus 1, 1, 1 plus 1, 2, 1 plus 2, 3, 2 plus 3, 5, 3 plus 5, 8, and so on. So this is a simple function which receives n, and it checks if n is either the 0th term or the first term. In that case, it will return n. Otherwise, it will first find n minus 1th term, then find n minus 2th term, then add these two terms and return the sum. Let us see the time complexity of this function. So this is the 0th term, this is the first term, this is the second term, this is the third term, 4th term, 5th term, 6th term, and so on. Let us assume that we want to find the 5th term of Fibonacci. To find the 5th term of Fibonacci, we will call this function for n equal to 5. When we call this function for n equal to 5, then because this condition is not true, we will call the function for n equal to 4, and it will call the function for n equal to 3. So first it will call the function for n equal to 4, then it will call the function for n equal to 3. Whatever these two functions return, it will just add these two numbers and return it to the calling function. In the next level, when the function is called for n equal to 4, then because 4 is also not equal to 1, so 4 will first call the function for 3 to find the third term of Fibonacci, then it will call the function for n equal to 2 to find the second term of Fibonacci. Same goes for n equal to 3. It will first call the function for 2, then call the function for 1. Similarly here, it will first call the function for 2, then call the function for 1. Similarly here, it will first call the function for 1, then for 0. When the value of n is either 1 or 0, then it will hit this terminating condition and return the value of n itself. It means that from here, the function will return 1. From here, the function will return 0. From here also, the function will return 1. Now this function where n is 2, it will add the two values that it has received from the function that it has called, and it will do 0 plus 1 1, and it will return 1. 1 represent the second term of Fibonacci, which is also correct because the second term of Fibonacci is 1. Now the control will come to the function where n is 3. It will just add these two numbers 1 plus 1 and return 2. Similarly, the 2 here will first call the function for 1, then for 0. The 2 here will also call the function for 1, then for 0. Now this 1 will return 1. This 0 will also return 0. And 1 plus 0 is 1, so it will return 1. And then this function will return 2 plus 1, that is 3. Similarly, this 1 will return 1, this 0 will return 0, 0 plus 1 is 1, this 1 will return 1, 1 plus 1 is 2. Then the execution control will come to the function where value of n is 5, which is the initial function that the calling function has called. This function will add 3 and 2 and it will return 5 to the main calling function. So the fifth term of Fibonacci will come out to be 5. That is also correct. You can see that one problem is getting solved multiple times. For example, here we have already found the third term of Fibonacci, but then we are recomputing the third term of Fibonacci here. Similarly, the second term of Fibonacci is computed here. It is also computed here. It is also computed here. So every time we receive a value n, we find the nth term of Fibonacci from scratch. We recompute it from scratch. This is called overlapping subproblems. It will be discussed more in dynamic programming course. If you have to find the time complexity of this function, how will you find the time complexity of this function? Let me just rub the return values so that there will be less cluttering. Now we can say that every node in this tree represents a function call. This tree is called function call tree. What is the height of this tree? We can say that the height of this tree is order of n. 5, then 4, then 3, then 2, then 1. So if it is n, then n minus 1, n minus 2, n minus 3, n minus 4, it will go all the way up to 1. Therefore, the height of this tree will be n. Now the height of this tree is n, and this tree is fairly balanced. So what can we say about the number of nodes in the tree? If the height of the tree is n, and if the tree is a complete binary tree, then the total number of nodes in the tree is 2 raised to the power n. But here the tree is not complete. So if the tree is balanced, then the number of nodes in the tree may not be exactly equal to 2 raised to the power n minus 1, which is the case in a complete binary tree. But even in a balanced binary tree, the total number of nodes will be big O of 2 raised to the power n, if n is the height of the tree. Now you must have noticed that in the tree questions, n represent the number of nodes in the tree. So wherever you are dealing with the height, you call the height as log n. If you look at it the other way around, that if the height is k, then total number of nodes in the tree will be 2 raised to the power k. So here n represent the height of the tree and total number of nodes in the tree will be 2 raised to the power n. So this is the function which is getting called 2 raised to the power n time. And every time this function is called, this function will take constant time because this function is performing one condition check and this function is performing one addition and this function is making two other function calls. So the total time taken by this function is constant because this function is called order of 2 raised to the power n time. So the total time complexity of this function is some constant into 2 raised to the power n, which means order of 2 raised to the power n. And this is an exponential time taking function. You can also write a non-recursive version of this Fibonacci function, which will take linear time. Linear time function will take order of n time to find the nth term of Fibonacci, whereas this recursive function is taking order of 2 raised to the power n time to find the same nth term of Fibonacci. Sometimes we do not understand the gravity or the difference between these two time complexities, one being linear and second being exponential. If n is 10, then the first function will take order of 10 time, whereas the exponential function will take 2 raised to the power 10 time. Now understand it this way, that something which can be computed in only 10 seconds using a linear time function or the first function, we have written a function which will find the exact same term, and our function will take 2 raised to the power 10, that is 1024 seconds, which means that a work that can be done in just 10 seconds We have written a code that will do the same work in 17 minutes. Now every second is translated to money. So the exponential function is consuming 100 times more resources for just a value of n equal to 10. When n becomes equal to 15, then it will be consuming more resources. So this is how bad the exponential time complexity is. So now we have understood how to find the time complexity of a piece of code. In the next video, we will be taking a lot of questions related to finding the time complexity of a piece of code. Thank you.